All right, in this video I want to take a look at the um, quadratic approximation to a function and come up with a couple of different ways of deriving it. So I'll shut myself off so we can see what we're doing, and here we go. Um, the first way that I'm going to do this is building on the methods that we used to look at the error approximation for the the error bound for the linear approximation. Um, This is a method that I didn't really understand as a student, and so when we got to calculating error bounds, I had written it off. I had another way of doing it, and that was good enough, but the other way, which I'll show you in a bit, doesn't lead to the error bound calculation. So here we go. This statement right here was what we calculated, that the difference between f and b is this thing. We did an integral two different ways in the previous video. All right, so I'm going to move this over to the other side and describe the function as the linear approximation plus this fudge factor. Actually, I guess it's not a fudge factor, it's a fudge term. Factors are multiplied, this is added, so a fudge term. What I want to do is I want to get a better understanding of this thing. So I want to do this integral, or at least attempt to do this integral, and see what we can do. So I'm going to do this by parts. So I'm going to let u equal f prime. So right, by parts, you're starting with the integral of u dv. So u is f double prime of t, and dv is whatever's left, x minus t times dt. So I take the derivative of u to get du, and the derivative of the second derivative is the third derivative times dt. And integrating dv to get v, so I integrate x minus t dt to get minus x minus t squared over 2. Okay, so plugging that in, the integral of u dv is u times v minus the integral of v du. So this is the first stuff. I'm not touching that. So the integral here, there's the u times v evaluated between b and x minus the integral of v du, and the minus sign comes along. Sorry, u dv v du. Yes, the minus sign comes along with the v, and the du is that. So anyway, plugging in the x and the b and subtracting. So I've got an x plugged in here and an x plugged in there. I got a b plugged in here and a b plugged in there. The x minus x is 0. That's going to turn into that 0 right there. I'm also, this minus is becoming a plus. Okay. So I end up at this stage right here, and I notice that what I've done now is I've got the function f is equal to this constant plus this linear piece plus this quadratic piece. So I have a quadratic function here plus some fudge term, something that's making this work so that it's exactly equal to f of x, but this right here, this polynomial, is an approximation to this function. Well, let's see what we mean by it's an approximation. First of all, we're going to call it the second Taylor polynomial. Right? I'm going to call it t sub 2 of x. It's just that f of b plus f prime of b times x minus b plus f double prime of b divided by 2 times x minus b squared. Okay. So notice here what the properties are. One is that if I plug a b in here, then I would plug a b in for this x and a b in for that x, and I end up with that it's just equal to f of b. That is, this second degree polynomial agrees with the function at x equals b. Okay. Likewise, if I take the derivative, looks like this, then plug in b, so t2 prime of b is this, which is f prime of b. That is, t2 and f agree with their first derivative. So the derivative of t2 and the derivative of f agree at x equals b. And likewise, if I take the second derivative of t2 is just this constant here, and when I plug in a b, I just get f double prime of b, so that t2 and f agree on their second derivatives. Probably not the third derivatives, because the third derivative of t2 is going to be a constant 0, and it's possible, but unlikely that f is going to have such a third derivative. But the quadratic approximation agrees, at x equals b, agrees with the function, agrees with the derivative, and the second derivative. Okay. Now, as I said, there's another way to approach this. Here's the way I would have done it as a student, which then doesn't lead to any understanding of where the error comes from. We'll have to come back to the method we just talked about to look at where the error in the approximation, how we calculate that. But here's the way I would look at it. I want a polynomial. I want a polynomial that agrees with the function at b, that agrees with the derivative of the function at b, that agrees with the second derivative at b. So it's like, okay, I'm centering this whole thing around b, so I'm going to write the polynomial centered at b. So a plus b times x minus b plus c times x minus b. This is a second degree polynomial, which is written in a way that's easy to figure out what's going on at x equals b. Right? So the thing is, I want f of b to equal p of b. Well, p of b, you can plug it in. You can plug in an x there, plug in a b there, and a b there, and I've got this. That turns into a 0. That turns into a 0. So I've got a plus 0 plus 0. And so a, this is the only thing left here is a, that's got to equal f of b. Likewise, if I take the derivative of this thing, I want the derivative of this thing at b to equal the derivative of f at b. So the derivative of this thing, the constant goes away. This is just going to be b times 2c, right there, b times 2c times x minus b. So when I plug a b in, it's b minus b. B minus b is 0, and this capital B has to be f prime of b. So the polynomial, I'm creating it here. I know a has to be f of b. I know that capital B has to be f prime of little b. And now I got to figure out what c is, and I'll do that using the second derivative. So I take the second derivative of b, of f, that's got to equal the second derivative of p. But the second derivative is just 2c. It is by the time you got here with this, the linear part, this was an x minus b. It's already got the b plugged in. But so the second derivative of this quadratic polynomial is just 2c. So 2c has to equal the second derivative of f at b. And so c is the second derivative of f at b divided by 2. And I end up with this polynomial looking just like this, which is what I ended up with. Is it still on the top of the screen? No, it's not, but it's the same thing. This is the same as T2. So I could always generate these polynomials as a student, because it's like, well, you give me enough information, you give me all this information about what you want to have happen, I can figure out what coefficients are needed to do that. But then when it comes to the point of how do I know how far off my quadratic approximation is from the actual function value, right? If I'm not plugging in b, if I'm plugging in something else, the approximation is wrong. But how wrong is it? Probably it's pretty good. So this other method, using that integration by parts, right? I have that the actual function is not almost equal to, it is equal to the quadratic approximation plus this stuff. So this stuff is the error. And I will talk about that in another video.